Welcome to the channel of the Institute of Microproduction Technology. I'm Lara Kohr, a research assistant in the Department of Micro and Nano Integration. Today I would like to introduce you to the CRC oxygen-free production. Processes in the metalworking industry are still carried out in the presence of oxygen. The resulting permanent oxidation of the metal surfaces mainly acts as a detrimental factor in production. Even in conventional protective gas atmospheres and in technical high vacuum, sufficiently high oxygen concentrations are present that contaminate the surfaces. Due to the presence of oxygen, there is an unexploited potential of technical possibilities in metal processing, which affects almost all production processes. An oxygen-free environment is created using silane-doped inert gas. The reaction between silane and oxygen in the inert gas produces oxygen partial pressure less than 10 to the power of minus 23 bar, achieving a practically oxygen-free atmosphere at ambient pressure. This environment approximates an extremely high vacuum, similar to the conditions found in outer space. This is why we talk about an extremely high vacuum adequate atmosphere in terms of the oxygen content. Consequently, an oxide monolayer forms only after several hours to years depending on the type of metal. This means that during metalworking processes, no new native oxide layer are formed, making the process effectively oxygen-free. Here at the Institute we focus on two-wear protection. We study existing coatings for their behavior in extremely high vacuum environments and developing novel coatings to enhance the functionality of tools. It introduces a novel approach using atmospheric pressure plasma treatment in extremely high vacuum adequate atmospheres to create coatings to deoxidized surfaces without oxygen inclusions such as carbides or nitrides. To allow our research under different defined atmospheric conditions without unwanted exposure to air between different process steps, an analysis line has been established inside two coupled glove boxes. Firstly, a plasma jet from PlasmaTreat can be used to completely remove the oxide layers. After that, a coating can be applied. The silane concentration can be varied within the glove box. Depending on this, experiments are carried out for in situ coating using reactive gases. The absence of an oxide layer on the base substrate allows higher diffusion between the material and the coating, which is hoped to improve adhesion. A nano-denter from Hysotron is used to analyze the mechanical properties such as hardness and the modulus of elasticity. This also includes scanning probe microscopy, which allows the roughness of the surface and the position of the indents to be determined. Another system in the analysis line is the ball-on-disc tribometer from Bruker. The coefficient of friction can be determined by applying a defined normal force and measuring the tangential force. In addition, the coefficient of wear is determined by analyzing the resulting friction drag. This allows conclusions to be drawn about the tribological properties. By adding a temperature chamber, tests can be carried out from room temperature up to a high temperature range. High-resolution images of the surface and chemical composition of the coatings are examined using scanning electron microscopy with X-ray spectroscopic analysis. Ellipsometry is used to measure the thickness of the oxide layer in coatings. Further analytical methods are made possible by the collaboration with the CRC. I hope I was able to give you an impression about the potential of oxygen-free production. Subscribe to this channel for more videos about the Institute.